Вроде включит. Хорошо. Okay, the previous lecture we introduced the functor K1 for Banach algebras and calculated the K1 group for some concrete algebras, in particular for the algebra of bounded operators on the Hilbert space, for the algebra of compact operators, and for the Kalkin algebra. And today we will study some properties, some general properties of the functor K1. Well, first of all, let's introduce some notation. Suppose we have a ring R. As usual, we don't assume that R is unital. We have the canonical map epsilon, the augmentation map from the unitization of R to the integers, given by the following formula. And we have an obvious map acting in the opposite direction, that's denoted by eta, from the integers to R plus, which takes every k to k times the identity. And let's also denote by S the composition of these two maps. So S acts from R plus to itself, and S is just eta epsilon. So clearly this is a ring homomorphism, and in some sense it takes every element in R plus to its scalar part. This element goes to this one. So that's why I denote it by S. So it takes every element to its scalar part. Let's also recall that at the previous lecture we defined the group GL and plus of R to be the kernel of the induced map, also denoted by epsilon, from GLN of the unitization of R to GLN of Z. So this is a normal subgroup in GLN of R plus, and we observed that if R is already unital, then this group is isomorphic to the usual group GLN of R. And the isomorphism is very concrete and is, of course, natural in R. And so this is the reason why we will often denote this group simply by GLN of R. So we drop the plus sign. And as a result, we see that GLN of R is defined for any ring R, not necessarily unital. Okay, let's now observe that we have the following two maps. We have two maps, actually two retractions. From GLN of the unitization, GLN of R plus, onto GLN of R. Let's denote them PL and PR. And they act as follows. PL takes A to S of A inverse times A, and PR multiplies by S of A inverse on the right. So clearly both maps indeed take GLN of R plus to this subgroup, simply because, well, the composition of epsilon and S equals epsilon just by construction. And so if we apply epsilon, for example, to this expression, we obtain the identity. So this matrix indeed sits in this kernel. And similarly, this one also sits in here. And clearly, if A is already in this subgroup, then S of A inverse is the identity, and we get A. So they project this group onto this subgroup. Let me write it explicitly. So the restrictions of these maps are the identity maps of GLN of R. Well, in general, they are not group homomorphisms. They are not group homomorphisms, but nevertheless, they are retractions onto this subgroup. Let's call them the normalization maps. Normalization maps. So each of them normalizes a matrix. In some sense, it normalizes the matrix by reducing its scalar part. So the scalar part of this matrix and of this matrix is trivial. So this is a useful, rather useful tool. We will use it several times today and maybe at the next lecture as well. And also let's adopt the following convention. Of course, we are mostly interested in algebras over the complex numbers. So if we work with k-algebras, actually this works over any commutative ring. So in the setting of k-algebras, we replace everywhere in this construction the integers by the base ring k, replace z by k, and of course we replace the ring unitization r plus z by k unitization r plus k. And of course we are mostly interested in the case where k is the field of complex numbers. Okay, so let's now look at some properties of K1. First of all, let's show that K1, in contrast to K0, K1 is insensitive to the unitization. So we have the following proposition, proposition 1. Suppose that A is a Banach algebra. And let's denote by I the inclusion map of A into its unitization. So I claim that I induces an isomorphism of the groups K1. The induced map I star from K1 of A to K1 of A plus is an isomorphism. To prove this property, let's draw a picture. So we first of all look at infinite matrices, GL infinity over A, and GL infinity over A plus. So this is a subgroup here. So the inclusion, let's know the inclusion by J. Now K1 of Y is by definition the quotient of GL infinity of A, modulo roughly the component of the identity. So we have the quotient map here, and similarly for the A plus, K1 of A plus. So these are the quotient maps. And of course the canonical map from this group to this group is induced by the inclusion of this group into this one. So here we have I star. Let's now apply one of the two normalization maps. For example, we can take the right normalization. P of A is A times S of A inverse. Again, we remember that this is not a group homomorphism, but nevertheless, it is obviously continuous on GLN of A plus for every n. So P is continuous on GLN of A plus. So it takes homotopic elements to homotopic elements, and as a result, it induces a map between the quotients from here to here. So it introduces map, let's denote it by P tilde from K1 of A plus to K1 of A, which acts in this direction. Well, since the composition of P and J is the identity map, just the construction, when we descend this to the quotients, we see that the composition of P tilde and I star is also the identity map here. And so in particular, I star is a monomorphism. To show that I star is surjective, let's observe that for any matrix A over invertible matrix over A plus, in GL infinity of A plus, if we apply epsilon to A inverse, then this matrix is homotopic to the identity matrix over the complex numbers, for the simple reason that GLN of C is path connected for every n. So every scalar matrix can be connected to the identity matrix. GLN of C is path connected. If we now apply eta, so this is our eta, we see that S of A inverse is homotopic to the identity matrix now in GL infinity of A plus. And multiplying by A, we deduce that S of A inverse is homotopic to A in GL infinity of A plus. So as a result, we see that every matrix in GL infinity of A plus, every matrix over A plus is homotopic to a matrix over A, which more exactly to a matrix which, to a normalized matrix, which comes from K1 of A. And so this implies that I star is an epimorphism, this surjective. And this completes the proof. As a simple corollary, we can now prove the result which was announced already at the previous lecture. We can now easily show that K1 of A is abelian for every A. Moreover, we can say the following: it is abelian, and if we take any two elements A and B in GL infinity of A, then the product of their classes in K1. So by definition, this is of course the class of their product. But I claim that it is also the class of their direct sum. This is a diagonal, block diagonal matrix. Well, to make it more correct, I assume that they are in the same GLN of A, where n is finite, because the direct sum operation is well defined only on finite matrices. Well, indeed, why is it so? We already know that we already have this isomorphism, so we may assume, without loss of generality, we may assume that A is unital. We may assume that A is unital by proposition 1. And let's now recall Whitehead's lemma. Actually, we had two Whitehead's lemmas. And now I mean the first one, which is about the second one, which is about homotopy between block diagonal matrices. So this lemma implies, actually it states that AB plus the identity matrix of the same size is homotopic to A plus B. And A plus B in turn is homotopic to B plus A. And for the same reason, B plus A is homotopic to B A plus 1. And that's it. So this completes the proof. So we see that AB, the class of AB in the group K1 is the same as the class of A plus B and the same as the class of BA. So the group is abelian. At this point, it will be useful to relate this property to algebraic K-theory. So a little remark. We can define the algebraic group K1 away. Let's denote it in this way. So usually this group is defined to be the maximal abelian quotient of the group JL infinity away. That is the quotient modulo the commutator subgroup. Well, of course, this construction makes sense for any ring, not necessarily for a Banach algebra. This makes sense for any ring. And if now A is a Banach algebra, we already know that K1 away, the Banach algebraic K1 away is abelian. And just by definition of the algebraic K1, we see that we have a canonical map. So since K1 of A is also abelian, we have a canonical homomorphism from the algebraic K1 of A to Banach algebraic K1 of A, which extends the identity map on matrices, on JL infinity. This is the so-called comparison map. Comparison map from algebraic K-theory to Banach algebraic K-theory. In general, this map is not an isomorphism. This is not an isomorphism. Actually, this is not an isomorphism already in the simplest case where A is the complex numbers. Well, indeed, we already know from the previous lecture that K1 of C is trivial. But on the other hand, the algebraic K1 of the complex numbers is not trivial and is isomorphic to the multiplicative group of non-zero complex numbers. And the isomorphism is very concrete. It is induced by the determinant. So the determinant of every commutator matrix is 1. Already from this observation, we see that this quotient is non-trivial. And actually, it is isomorphic to non-zero complex numbers. In fact, there is a rather advanced theory about parallels between algebraic K-theory and Banach algebraic K-theory. In particular, about some obstructions for this map to be an isomorphism. In particular, there is a deep theorem due to Suslin and Wojcicki, which says that this map is an isomorphism. This map is an isomorphism for every stable C-star algebra. For every stable C-star algebra A. This is a theorem due to Suslin and Wojcicki. 1992. Okay, let's now come back again to properties of K1. Our next result, proposition 3, K1 is a homotopy invariant. The functor K1, so this functor is defined on Banach algebras, and we now know that it takes values, it has values in the category of abelian group, This functor is homotopy invariant. In the same sense as K0. So it takes, if you have two homotopic homomorphisms between Banach algebras, then they induce the same map between the groups K1. And the proof is essentially identical to the proof for K0. Identical to the case of K0. It's a little exercise, which is fairly trivial. Just look at the proof for K0 and see that this absolutely the same argument works for K1. This is very easy. Actually, this is not surprising at all because the K1 is defined in terms of homotopy. So we quotient out, we identify homotopic matrices in GL infinity of A. And so it's quite natural that this functor is homotopy invariant just almost by its very definition. As a corollary, we see that, for example, if A is a contractible Banach algebra, if A is contractible, then K1 of A is 0. Well, in fact, the functor K1 shares many properties with K0. For example, and this is a good exercise, the functor K1 is shows as a functor K1 is half exact, split exact, continuous, it commutes with inductive limits, stable, is invariant under multiplication, under tensoring by compact operators. Actually, this is more or less immediate from the continuity, just like in the case of K0. Also, it preserves products. And in fact, this can be considered as a special case of split exactness. And it is invariant under taking the opposite algebra. Well, I wouldn't say that this is trivial. This is not entirely trivial. But the overall plan of the proof is the same as in the case of K0. So the exercise is not trivial, but it is reasonable. So just analyze the proof for K1 and try to extend it to for K0 and try to adapt it to the case of K1. In fact, we will shortly we will obtain all these properties as simple corollaries of a general theorem, which will enable us to reduce K1 to K0 for Banach algebras. So actually, there is no need to prove it directly. It is useful, but actually formally it is not necessary because we will see that this is a simple corollary of a general theorem relating K0 to K1. Okay. Now our next goal. Our next goal is to introduce a very important tool in K theory, namely the indexed map. The indexed map in K theory. Well, first we'll define this map in the pure algebraic setting, that is in the case of arbitrary rings. Look at some properties of this map, and then apply it to find a relation between the functors K0 and K1 for Banach algebras. To begin with, let's start with the following lemma, which is essentially a non-unital version of Whitehead's lemma about lifting invertibles. Suppose we have a surjective ring homomorphism from R to S. Surjective ring homomorphism. And A, let A be a matrix in GLN of R. I claim that the following block diagonal matrix A plus A inverse lifts to GL. Oh, sorry, it was in GL of S, of course, in the quotient. Yeah, in S. And I claim that the block diagonal matrix A plus A inverse lifts to an invertible matrix to an invertible matrix over R in GL to N of R. Well, let's recall that we already know this fact for unital rings and unital ring homomorphisms. So we proved it some time ago when we discussed algebraic properties of the functor K0. Now we will need it in the non-unital setting. And the proof is a simple reduction to the unital case. So first of all, let's lift this matrix A plus A inverse to a matrix, let's note it by V, over the unitization of R plus. So we know that this is possible. And then we normalize V, as denoted by U, the following matrix, the right normalization of V. So it belongs now to GL to N of R. And let's now see that this is exactly what we're looking for. So P of U. So we want that P of U is exactly A plus A inverse. So P of U is P of V applied multiplied by P of S of V inverse. Well, strictly speaking, not P, but P plus. So of course we extend everything to the unitization. So the first element is just A plus A inverse. And let's now observe that actually P plus and S commute. This is a little exercise here, but it is almost immediate from the definition of S, the scalar part. And this is the inverse to this matrix. This is A inverse plus A. It is normalized. What is important, and this matrix is already normalized, so S applied to this matrix is 1, and we get A plus A inverse. And that's it. So this completes the proof. Okay, so let's now define the index map. The index map is associated to any ring extension. So we take a ring extension, I, R, and S. So the inclusion of I into R will be a little I, and this will be a little p. So this is a ring extension. By the way, let's observe, now let's make useful observation that every ring extension gives us the following two exact sequences. The first one is obtained by taking the matrices and by add matrices. So this sequence is obviously exact, and it will be also exact if we take here the unitizations of R and S. So first of all, we observe that we can apply the unitization here and here in the original extension, and then we take the matrices, and we still get an exact sequence. And the second exact sequence looks as follows. It is about GLN of I, GLN of R, and GLN of S. So both sequences are exact. This is more or less immediate from the definition of GLN. Of course, I don't claim that the second sequence is exact at GLN. In general, not every invertible matrix can be lifted to R, but it is exact here and here. Okay, so let's now construct the index map. So we define a map from GL infinity over S to K0 of I as follows. So first of all, we take an element A in GL M of S. So we take an element in GL infinity of S, find M such that it sits in this subgroup of finite M by M matrices, and find an element B. This is sort of auxiliary element, also in GL N of S, possibly of a different size, such that the block diagonal matrix A plus B lifts to an invertible element, lifts a matrix U in GL M plus N of R. So by the previous lemma, this is always possible, and actually we can let B equal A inverse. But for technical reasons, we don't assume that B is exactly A inverse, because in some concrete situations, it will be more convenient to take another auxiliary matrix B. But anyway, this is possible by the lemma. Let's now observe that if we apply P to the matrix U, this is A plus B, and clearly this matrix commutes with the matrix 1M, so this is 0. Let's recall that 1M denotes the identity in the group GLM of S in this group. So as an element in this group, this is 1 plus 0. Let me write this explicitly. 1M is identified with 1M plus 0 in GL M plus N. This is obviously true because, well, this matrix is just A plus B. This commutator is nothing but P plus applied to the commutator of U and 1M, now calculated over S. So this is 0, and now by looking at the first exact sequence here, we see that this commutator of U and 1M actually has coefficients in I. So this implies that this commutator sits as a matrix over I. It sits here. If we multiply this commutator by U inverse on the right, we see that 1 U1 U inverse minus 1 M is also a matrix over I. Also, both matrices here are clearly idempotents over I plus. So 1M and U1M U inverse belong to idempotents over I plus. So clearly this is true for the first matrix, and since this difference has coefficients in I, it follows that this first matrix U1 U inverse is also a matrix over the unitization of I. And so we can now take their K-theory class, the K-theory classes, and calculate their difference. Well, I need some space. Let me write it here. This will be our definition of the index map. We let the index of A be the following element in K-theory of I, U1M U inverse minus 1M. And it sits in K-theory not only of I plus, but actually of I, because the difference of these matrices has coefficients in I. Actually, this is one of our explicit descriptions of K1 for non-unital rings. Okay, so this is our construction of the index map. Of course, if we look at this formula, we see that there are several auxiliary choices here. A priori, the right-hand side of this formula depends not only on A, but it depends also on M, because we can increase M, replace, for example, M by M plus 1, and consider the same matrix as a matrix in GL M plus 1 of S. Formally, the right-hand side depends on M, which is not good. Also, it depends on B. We have chosen B here. And it also depends on the lifting U, which is also not unique. Before we study the properties of the index map, we have to show that it is well defined. Proposition 1, the index map is well defined. So the proof will be divided into several steps. As the first step, let's show that it doesn't depend on the choice of the lifting of A plus B. So it doesn't depend on the choice of U. Independence of U. So let's take two different elements, two different liftings, U and V, in GL M plus N over R, and suppose that P of U equals P of V equals A plus B. Let's now look at the element UV. Which of them? VU inverse. So what can you say about this element? Well, it's in the kernel of P. And now we look at the second exact sequence here. So this element is in the kernel of this map. So actually it is contained in here. So it is contained in GL M plus N over I. And if you now conjugate the first element which appears in the definition of the index conjugated by VU inverse, U1M, U inverse, UV inverse. And multiply all these elements, what we get is V1M, V inverse. So we see that this element and this element are similar. U1, U inverse is similar to V1, V inverse in GL M plus N of I plus. So the K-theory classes are the same because they are similar, and so as a result, we get the following equality. So in other words, if we replace U by V, we get the same element in K0 of I. And this shows that our definition doesn't depend on the choice of the lifting or the choice of U. Okay, now the second step is to prove the independence on M, on the size of the matrix A. So if we consider that as a matrix of a bigger size, the right-hand side of this formula doesn't change. Actually, again, for technical reasons, we prove simultaneously the independence of M and N. Of M and N. So what we want to do, we want to show that the right-hand side of our formula, well, let's denote this formula, for example, by star, the formula which defines the index map. The right-hand side of this formula doesn't change. Doesn't change if we replace A by A plus 1I, say, for some natural number I, and B by B plus 1G for some natural numbers I and G. In other words, increasing the sizes of the matrices doesn't change the right-hand side of our formula. Okay, so let's write explicitly what we already know. So the matrix U, let's write it explicitly as a 2 by 2 matrix of the following form. So it goes to A, B under the map P. We want to find a matrix. We want to find a lifting of the block diagonal matrix A plus 1 plus B plus 1. And let's try the following one. Let's denote by U hat the following matrix U1, 1, 1I, U2, 2, 1J. Well, it's clear that this matrix indeed goes to A, 1I, B, 1J. But in general, this matrix is not invertible. So to make an invertible, I put U1, 2 here and U2, 1 here. In other words, this matrix is obtained from this matrix plus the identity matrix by interchanging the first and the second column, and the first and the second and the third column, and the second and the third rows. So U hat is the matrix in GL M plus N over R. And now, what we want to do, so we want to show that if we replace in our definition of the index map U by U hat, so U hat, also we replace M by M plus I, 1 M plus I, U hat inverse, minus 1 M plus I. So we want to show that this is equal to the right-hand side of our formula, that is to the following element in K-theory. So we want to show that they are the same in K0 of I. To show that they are the same, we rearrange the blocks here. More exactly, we consider a scalar matrix, as denoted by T. It is a scalar matrix of the following size: M plus I plus N plus J, or the complex numbers. Well, I can write it explicitly, but it is probably more understandable if I describe the respective operator. So it corresponds to the following operator on our space Cm plus Ci plus Cn plus Cj, the operator which flips these two summands. So this is an invertible matrix of the respective size. And if you now conjugate U hat by this matrix, T U hat T inverse, so conjugation by T, it's easy to see that conjugation by T interchanges the second and the third columns and the second and the third rows. So as a result, we get U plus 1, the identity matrix of size I plus j. The same is true for U inverse, U hat inverse. U inverse plus the identity matrix of size I plus j. And if we conjugate this matrix, 1m plus I, we get we get 1m plus 0 of size I plus 1 of size n plus 1 of size j, or plus 0 of size j. Is that correct? No, this is not correct, of course. Sorry. Here we have 0 of size m, and here we have 1 of size I. Yeah, now it is correct. Okay, so now to calculate this the first element in this formula, we conjugate it by T. The K-theory class will not change because, of course, conjugating by scalar matrices doesn't change the K-theory class. And of course, the conjugation of the product is the same as if we conjugate every element and then take their product. So T times this element times T inverse is the following. We simply multiply this matrix, and this matrix. 1 m plus 0 plus 1 I plus 0 and this one. So what do we have? Looking by comparing the sizes of the matrices, we see that we can first of all multiply this, this, and this, and then take the direct sum with the product of this matrix, this one, and this one. So in summary, we get the following. This is U times 1 plus 0, U inverse. And if we multiply these three matrices, clear we have 1 plus 0. 1 I. Okay, so as a result, we see that this matrix, this matrix represents the following element in K-theory. So you had 1m plus I, you had inverse minus 1m plus I. So conjugation doesn't change the K-theory class. So this is U 1m U inverse. Here again, for brevity, I denote 1m plus 0 simply by 1m as before. Plus the class of 1i, this is the second direct summand, and 1m plus I is the difference of 1m and 1i. So these two guys cancel, and as a result, we get exactly the right-hand side of our formula. Okay, so this shows that our definition of the index map doesn't depend on the choice of M and N. And the final step in the proof of our proposition is that, step 3, is to show that the right-hand side of this formula doesn't depend on the choice of the auxiliary matrix B, independence of B. Okay, so let's take another matrix. Suppose, say, C is a matrix in GLN, well, in general of different size, N over S. And this matrix is such that there exists a matrix V in GL n plus n of R, such that P of V is A plus C. N prime here, n prime. But actually, we may assume from the very beginning that n equals n prime equals n. We may assume that n prime equals n. Because we have already proved the independence of n. So if they are not equal, we simply increase the sizes of the matrices B and C to make them equal. Actually, it's enough to increase the size of only one of them, and so we get matrices of the same size, and so we may assume from the very beginning that the sizes of B and C are the same. So by step 2. Okay. Roughly what we are going to do. So formally, we have to show that this formula doesn't change if we replace U by V. But this is not convenient. For convenience, the first step will be to replace, to modify somehow V to a more manageable matrix, satisfying the same property. So we will try to change somehow the lifting V. We do it as follows. We observe that 1 plus B inverse C. So this is just the matrix which is obtained if we multiply the inverse of this by A plus C. So this is P applied to U inverse V. So since in the image of P star and the image of P star is easily seen to be invariant under conjugation by scalar matrices. P star is applied to just coordinate ways to every entry of the matrix, and clearly it takes so every scalar matrix over R plus states it stays where it is after we apply P. So as a result, this subgroup is invariant under conjugating by scalar matrices. Well, formally this is a little exercise, but this is very easy. And so it implies that if we interchange these two matrices by conjugating by suitable transposition matrix, we get that B inverse C plus 1M also belongs to the same subgroup. So we can write it in the form, in the following form. This is P applied to W for some W in GL M plus M of R. And so let's now consider the following element. Let's denote it by Z. Z will be the following matrix. It will be U plus 1 times 1 plus W. So we increase the sizes for our matrices by m, and so this sits in 2m plus n, 2m plus n over R. First of all, I claim that Z is also the lifting of the same matrix A plus C. Of course, not of the same matrix, but of the same matrix is considered as a matrix of a bigger size. Well, indeed, why is it so? P of Z is, so P applied to U is A plus B. And P applied to the second matrix is P of 1m is 1m. P of W is, where's W? P of W is B inverse C plus 1m. And multiplying these matrices, we get A plus C plus 1. Good. So this is another lifting of A plus C. And now we want to show that if we replace U by Z, we get the same element in K theory. In K0 of I. If we prove this formula, then we will see that the right-hand side of this formula calculated for A plus B, and the right-hand side of this formula calculated for A plus C are actually the same. So it doesn't depend on the choice of B. Actually, we will see that these two elements are, these two matrices are the same. Not only their elements in K theory are the same, but the matrices are the same. Why is it so? Well, let's calculate simply this matrix Z1, Z inverse is U plus 1m times 1m plus W times 1m plus 0 times now Z inverse 1m plus W inverse U inverse plus 1m. So if we now look at this formula, we see that if we multiply these three matrices, then W cancels and we get simply 1 plus 0. That's the reason why we replaced V by Z. If we work with the original matrix V, then this trick doesn't work. So we replaced V by Z exactly for this to work. So we multiply these matrices and we get U plus 1 times 1 plus 0 times U inverse plus 1, which is of course nothing but U1m U inverse plus 0. And we say that these two matrices are essentially the same, modulo adding the 0 matrix here. Clearly, so they present the same element in K theory, and we get formula 2. And this completes the proof of proposition of our proposition. So we have proved that the index map is well defined, so it doesn't depend on the choices of B, M, N, and of the lifting U. Our next goal is to show that index is not just a map, but is actually a group homomorphism. Why is it so? We start with, again, with an auxiliary lemma. I claim that the index of AB equals the index of A whenever B whenever B has a lifting, whenever B comes from GLN of R. From GL infinity of R. Well, the proof is more or less straightforward. Again, we choose a lifting for A plus, not plus B, because B is already in use. Well, let's slightly change our notation in the definition of the index map. So A sits in GLM of S. We find A prime in GL. Actually, we can take the same M. We already know that this doesn't depend on M of S, such that A plus A prime comes from an element in GL to M over R. Okay, so now we know that B comes from GLM of R. So there exists, by assumption, there exists an element C in GLM of R such that P of C equals B. It's very easy now to find the lifting for AB. For AB plus A prime, namely AB plus A prime, comes from the following element: U multiplied by C plus the matrix, the identity matrix of size M. It's clear from the previous line. Follows from the fact that C goes to B. So this is a lifting of AB plus A prime, and by definition of the index map, we deduce that the index of AB is the following element in K theory. So we take this matrix U, C plus 1, M, multiplied by 1M, plus 0, and by the matrix U inverse, and minus 1M. Now we calculate, oh, sorry, I forgot one matrix here, sorry. 1M plus 0, and then we have to take the inverse of this product. So C inverse plus 1M, U inverse, minus 1M. Okay, now we calculate this product. Again, if we look at the product of these three brackets, we see that the product is just 1 plus 0, so C doesn't matter. And we see that this is U, 1M plus 0, U inverse minus 1M. But this is nothing but the index of A, again by the definition of the index. And that's it. So this completes the proof of our lemma. As a corollary of our lemma, we see that the index of AB is equal to the index of A plus B. That is of the block diagonal matrix A plus B, for every pair of n by n matrices A and B. By the way, it's useful to compare this fact with our earlier result about K1. So we remember that AB and A plus B represent the same element in the group K1, provided that we work with a Banach algebra. Of course, at this point, we work with arbitrary rings. So this is only a formal analogy. Now, but if we imagine for a moment that we work with Banach algebras, there is a deep relation between this equation and the similar equation in K1. The point is that these two matrices are homotopic in GL infinity over S, and index is also homotopy invariant. We will see this shortly. So in the context of Banach algebras, index is homotopy invariant, and this explains where this formula comes from. But at this point, we work with arbitrary rings, so of course we don't have any homotopy arguments at our disposal, but we prove this purely algebraically. Indeed, AB, let's replace AB by AB plus 1. This is possible because the index doesn't depend on the choice of M. And represent this matrix in the following form. This is A plus 1 times B plus B. A plus B, yeah. A plus B times B plus B inverse. And this second matrix here comes from GL to M of R by Whitehead's lemma, by the non-unital version of Whitehead's lemma. And now our previous lemma implies that the index of AB plus 1 is equal to the index of A plus B. So this completes the proof. So we simply apply our lemma. Okay, now we are ready to show that the index is a group homomorphism. Proposition 3. The index which acts from GL infinity of S to K0 of I is a group homomorphism. Okay, so let's now take two elements in GL M of S. Again, we may assume that they have the same size, GL M of S. Find elements, auxiliary elements A prime and B prime, also in GL M of S. Again, we may assume that they are of the same size. And two invertible elements, two elements U and V in GL 2M of R, such that U is a lifting of A plus B. Sorry, not A plus B, A plus A prime, and V is a lifting of B plus B prime. So in other words, they are the elements which are involved in the definition of the index map. So the index of A is then U1M U inverse minus 1M, and the index of B is V1M V inverse minus 1M. So we want to find the lifting of A plus B plus A prime plus B prime. Of course, we can try U plus V. But U plus V doesn't work because U plus V goes to A plus A prime plus B prime. But this is not a big problem here. There is no big problem here because we can always interchange the second and the third summons by conjugating with a suitable scalar matrix. So as before, we let T, it will be a scalar matrix of size 4M. This matrix corresponds to the following operator. The operator which interchanges, which flips the third and the second direct summons. Then, if we apply conjugation by this matrix T to the element u plus v, we get a plus b plus a prime plus b prime. So again, by the definition of the index map, we can now calculate the index of AB. First of all, we apply our previous corollary and replace AB by A plus B. This is the index of A plus B. And we already have a nice lifting for A plus B plus A prime plus B prime. This is this element. So again, by the definition of the index map, this is the K-theory class of T times U plus V times T inverse. Oh, sorry. Not exactly. So we have to we take this matrix, then we multiply it by 1m plus 1m plus 0 plus 0. This is a convenient way of writing the matrix 1 of size 2m. And then we multiply by the inverse of this matrix, which is T inverse, T U inverse plus V inverse and T inverse. And minus 1 to m. So what's this? Again, we look here. First, we multiply these three matrices which are in the middle. And clearly, we simply conjugate this matrix by T. So these two summands will be interchanged. So we get. And also, at the same point, we can't forget about T, which is on the left, and T, which is on the right, because conjugating by scalar matrices doesn't change the K-theory class. So we simply forget about these copies of T, and we multiply the matrices which are in the middle, and we get U plus V times 1m plus 0 plus 1m plus 0 times U inverse plus V inverse. Minus 1 to m. Minus the identity matrix of size to m. Now we multiply these three elements. Okay, so probably I can now remove our construction of the index map. So what do we get? We just regroup the matrices. So first we see that the sizes of the matrices are compatible. That is, the underlined matrices are of size 2m, and doubly underlined matrices are also of the same size. So as a result, the product of these block diagonal matrices can be written as follows. This is U1 plus 0 U inverse. Direct sum V 1 plus 0 V inverse minus 1 to m. And this is almost the end of the story, because the first element here is just U1m U inverse. The second one is V1m V inverse. And 1 to m can be written as 1m plus 1m. these two summands give us the index of A, and these two summands give us the index of B. So in summary, we get the index of A plus the index of B. So the index is indeed a group homomorphism. Okay. I see it's time to finish. Anyway, let me briefly explain where we are going to and why do we need the index map. Why is it useful? Just a short announcement for the next lecture. We will see that the index map gives us the following exact sequence. GL infinity of R, GL infinity of S, then we have K0 of I, K0 of R, and K0 of S. So this is induced by I, this is induced by P, this is also induced by P, and here we have the index map. So remember that K0 is half exact. So before we didn't know what happens, actually can we extend this sequence of this three-term sequence to the left? Now we see that we can extend it to the left as follows. So we simply write the respective group GL infinity here, and we get such an exact sequence. Moreover, for Banach algebras, this exact sequence leads to two important corollaries. First of all, it leads to a very useful isomorphism between K1 of A and K0 of another algebra, which is called the suspension of A. So the suspension of A is, so the short way of writing the suspension is as follows. The algebra of C0 functions from the real line to A. So this is a very useful formula which reduces K1 to K0, and in particular this formula implies that K1 is indeed half exact, split exact, continuous, stable, and so on. And second, a second useful corollary for Banach algebras is that if you write the sequence explicitly for a Banach algebra extension, for a Banach algebra extension, I, A, B, we have a six-term exact sequence starting with K1 of I, then we get a map which is induced by the index map to K0 of I, so all these arrows are induced by I and P respectively, and here in the middle we have the index map, or more exactly the map which is induced by the index map after we quotient out the connected component of GL infinity of B. Moreover, actually we can extend this sequence infinitely to the left. We can define the groups K2 of A, K2, K3, and so on, and so put here K2 of B, K2 of A, K2 of Y, then K3 of B, and so on. So we can extend it infinitely to the left by suitably defining the higher K3 groups. But on the other hand, there is another fundamental result, the Bott periodicity, which tells us that K2 of B is isomorphic to K0 of B, and actually we can modify this sequence into a cyclic six-term exact sequence, which contains only 6 groups, K0 groups for the algebras of our extension, and K1 groups for the same algebras. Okay, so this is the explanation why we need an index map and why it is useful in K-theory. And also another announcement is that the index map, why is it called the index map? It is called the index map because it is closely connected to the threshold index. So this will also be shown at the next lecture. Okay, thank you.